Hi, let's go through section 6.1. Sorry, let me get a different pen. I don't want to use green yet. All right, so 6.1 is all about exponential functions. Exponential functions are not necessarily more difficult than anything we've done before, but you've probably never seen them before, so they're going to look a little weird because they're things that look like f of x equals 2 to the x power. So what's happening is our exponent is now the variable, okay? So we have to be a little careful. And when we start solving these exponential equations, we're going to have to use another new type of function called a logarithmic. And logarithmic functions are the inverse of exponential functions. The two kind of go hand in hand. So before we can talk about logarithmic functions, we're going to talk about exponential functions. And your textbook has this really pretty nice example of a bouncing ball. So think about the super balls that you used to play with as a kid. Suppose you are standing here and you have a ball in your hand, okay? And you drop that ball, or you toss it a little bit, and you let it bounce. So it hits the ground. And you remember super balls, they bounce back up, and they keep doing that. And each bounce gets a little bit shorter, and a little bit shorter, and a little bit shorter, until you can't really tell that it's bouncing anymore, but you know it still is because you can still hear it going da-da-da-da-da. Yeah, okay. So what the example in the textbook is saying is, let's suppose that we were holding our ball. We're just going to say for now the initial height is h. Each subsequent bounce is 2/3 the height of the bounce before it. So we started at h. That means the ball came up to 2/3 of that height on the second bounce. On the third bounce, it would be 2/3 of 2/3 of the height of the bounce before it. So this is bounce 1. This is bounce 2. The third bounce would be 2/3 of 2/3 of 2/3 h, and that's bounce 3. So our first bounce, let's say that we are holding our ball 3 feet off the ground. So let's say h equals 3. So the height of the initial bounce is 3 feet. The height of the first bounce is 2/3 times 3, or 2 feet. The height of the second bounce would be 2/3 times 2/3 times 3, or 2/3 squared times 3. And we can figure out that number. That would be 4/3 feet. The height of the third bounce, if we follow our pattern, is 2/3 times 2/3 times 2/3 times 3, or 2/3 to the third power times 3, which would be 8/9 of a foot. So if we keep counting, and we want a general formula for the nth bounce, that's going to be our initial height 3 times 2/3 to the nth power. So the exponential function is that h of n, the height of the nth bounce, is going to be equal to the height that we started with, which in this case is 3, times 2/3 to the nth power. So our variable is now in our exponent. This is the general form for an exponential function. In general, exponential functions look like f of x equals a times b to the x power. Notice our variable, and actually that's b to the kx power. Our variable is in the exponent. K is what we call a coefficient of exponential growth, or exponential decay, and we'll talk about the difference between those in a minute. And A is just like this h. It's just a part of the function. Okay, so let's talk about what exponential functions look like and what we're going to do with them. So the first thing I want to do is I want to evaluate. So let's let f of x be 2 to the x and g of x be 3 to the x. Let's find f of 0. Well, that means that is 2 to the 0. Now you may or may not remember that anything to the 0 power is 1, but it is. Any base to the 0 power always equals 1. So g of 0 is likewise going to be 3 to the 0 power, which is 1. All right. So both of these functions go through the point 0, 1. Let's evaluate this function at 1. F of 1 is 2 to the 1, and you may or may not remember, but anything raised to the first power is just itself. So f of 1 goes through the point 1, or sorry, f goes through the point 1, 2. If I take g of 1, I get 3, and it goes through the point 1, 3. So I'm going to pull up Desmos here for a minute, and we're going to take a look at the shape of these graphs. And I'm using Desmos because Desmos draws better than I do. Sorry, I should have had this done before I started. I wasn't sure I was going to do graphing, but we need to. Okay. So let's launch this calculator. And I'm going to start with 2 to the x power. Okay. And there are a couple of things I want you to notice here. First is that this function goes through the point 0, 1, like we already said it would, right? Remember, we talked about that just a minute ago. It also goes through the point 1, 2, like we said it would. So to find other points on this function, to graph it, you just need to pick other x's. So pick a different x, say f of 2. F of 2 is 2 squared, which is 4. So the graph goes through the point 2, 4. Now I want to talk to you about something like f of negative 2. Because you may or may not remember that any number raised to a negative exponent is the same thing as 1 over that same number raised to a positive exponent. So 2 to the negative 2 is actually 1 over 2 squared, or 1/4. So the graph goes through the point negative 2, 1/4. So if we go back to Desmos, we can see negative 2, 1/4. Lies on the graph. And we can see that 2, 4 lies on the graph. All right, I'm going to turn all of these points red, just so they match our graph. All right, now I'm going to put on this same grid line, the same set of axes, the line y equals 3 to the x power. And I'm going to make it a different color because orange is too close to red. Let's make it blue. Okay, if we compare these two graphs, and I'm going to zoom in a little bit by adjusting my axes. Actually, I'm not. I'm just going to do this. There we go. A little bit more. All right. So I've zoomed way in here, but what I want you to notice are a couple of things. One, notice both graphs go through the point 0, 1. So remember, the blue one is y equals 3 to the x. That's our g function on our notes. Notice both of them go through the point 0, 1. Let me zoom back out just a little bit more. Notice that f, which has a base of 2, goes through the point 1, 2, whereas g, which has a base of 3, goes through the point 1, 3. So what I'm showing you is that if you look at the graph, you can tell it's exponential because of a few things that are happening here. Exponential functions have a horizontal asymptote at the x-axis. In other words, they will never cross the x-axis. There's not any negative x's down here ever. Or sorry, no negative y's. We're going to talk about this in the terms of domain and range here in a minute. And if you need to find the base, look at x equals 1 and see where the function goes through that point, because x equals 1 will correspond to some multiple of the base. It'll depend on whether or not you've got an a, but it's how you figure this out. So let's talk about exponential functions in general for a minute while we've got this graph up here. Okay, let's see, how am I going to do this? Make this go away. I'm going to shrink this graph down a little bit. There we go. Okay. So you can see both my paper and my graph. And in general, exponential functions things that look like a function equals some number times some base to an exponent with a variable in the exponent. They will have the same basic shape. They will look like what we have on the screen there. If b is greater than 1. Okay? So I've got both 2 and 3 up there on my screen. If you've got a fraction for your base, so if b is less than 1, then they're going to be reflected horizontally across the y-axis. And I'll show you that in a second. But they all go through the point 0, 1 if A is 1. So we're going to, for this conversation, we're going to assume that A is 1. So we're really looking at f of x equals b to the kx power. All right. You can always figure out your base, because if x is 1, y is your base. All right, so that's the general shape of exponential functions. Later we're going to talk about logarithmic functions, and you're going to see they look different. But you need to be able to differentiate between exponential and logarithmic functions, because that's one of the things we want to do here. So let me just take off this blue graph, and I'm going to show you what it looks like when you've got a fractional base. So I'm just going to use 1/2 to the x power as my second function. And you can see that it looks an awful lot like 2 to the x, except it's reflected horizontally. So this function goes through still 0, 1, but now goes through -2, 2. And if I look at x equals 1, it goes through, or sorry, at -1, 2. At x is 1, it goes through 1/2. Okay. So all exponential functions have this same basic shape. What that means is, okay, the variables in the exponent. So your domain, you can put any number into an exponential function. So it's going to be the domain is all real numbers, or -infinity to infinity in interval notation. However, we can never get a negative number out of an exponential function, nor in actuality can we get 0. So y is always going to be greater than 0. Or in interval notation, that's going to be 0 up to infinity. Okay, that's the basics of exponential functions. What I need to talk to you about now, we're almost done. I just want to take a couple more minutes, and I want to talk about half-life. The half-life of anything is the length of time that it takes for half of anything to disappear. Now, most often we're going to talk about this in terms of radioactive isotopes, like, for example, a radioactive iodine that they use for medical imaging. And in that case, what we're talking about is the isotope of iodine that is radioactive decaying down to the non-radioactive isotope. The example I like to use is M&Ms. Let's say I have 10 M&Ms. The half-life of those 10 M&Ms would be however long it takes me to eat 5 of them, which isn't very long. And then the idea is a half-life never changes. So and the other thing is that this type of decay is exponential in nature. So if we're talking about the amount of, let's say, radioactive iodine that is left after some amount of time, t, the amount left is going to be however much we start with, multiplied by 2 to the -t over k. Now this 2 here tells you that we're really talking about a half-life. You may be thinking, well, but wait, 2 isn't 1/2, 2 is 2. You're right, but you see this negative sign up here? This makes it a decay problem, which means that we're talking about a half-life. Half will be gone. And the K is the half-life of our substance, whatever that substance might be. Let me find an example in the textbook. So let's say that we're using a certain drug. And its half-life is 4 hours. And let's say that a patient comes in with a concentration of 60 nanograms per milliliter of this blood. Or sorry, of this drug in their blood. And what we want to know is how much or what is the concentration of the drug in the patient's bloodstream after 12 hours. Now there's a couple of different ways to do this. The first thing I want to do just to demonstrate half-life is we're going to build a table. We're going to talk about hours. And I'm going to put in another column that says half-life. We'll talk about that in a minute. And then we'll fill out concentration. Okay, so when we first take the measurement, times 0. 0 half-lives have passed, and we know that my concentration is 60. Now let's say I take a measurement 4 hours later. Now 4 hours is 1 half-life. What that means is that half of what we started with, or half of what we had 1 half-life ago, is gone. So 60 divided by 2 is 30. So the concentration now is 30 nanograms per milliliter. At 8 hours, that's another 4 hours. So that's another half-life passed. So that's 15 nanograms per milliliter are left. Half of what we had before. At 12 hours, we've gone through 3 half-lives, and the concentration will be 7.5. You get the idea? At 16 hours, that's 1 more half-life, and I don't know what half of 7.5 is. I think it's 3.75, but I better check that. Seven 7.5 divided by 2 is, yes, 3.75. But to answer our question, the concentration in the patient's blood after 12 hours is 7.5 nanograms per milliliter. The generic constant, or the generic formula here for this is that the amount left after T hours is the amount that we started with, which is 60, times 2 to the negative T over the half-life, which is 4. Okay. Your book also talks about the natural base, the base E. I'm going to let you read about that. So look at the natural exponential functions on page 421. And your book also talks about continuously compounded interest on page 423. And I'm going to let you look at that as well, because I think this video is long enough. But if you have any questions, please submit them to the forum, and I'll be more than happy to answer them for you, or you can shoot me an email. I'll talk to you again soon.